This is AGNR 131 Soil Science Lab, and this is the lab exercise 3, part 1, where we actually run the soil hydrometer. We actually do the hydrometer method to determine soil texture. So you remember from the last video that we showed you how to go ahead and prepare the soil samples, and today we're actually going to run the two soil samples that we prepared from the last video. So first of all, you can see our samples right here. And this is kind of interesting. You can see that. This one I shook up, but you can see that they're not clear. The HMP did exactly what it was supposed to do. It's actually separated all the particles out, and the clay particles looks like they're still kind of hanging there in suspension because they're the smallest ones. So here's our two samples. Now let's talk about why we're doing this and what the hydrometer method actually shows and what's the principle behind it. So it's all based on density. So your sand, silt, and clay particles have different densities. This is why it was so important for us to actually measure exactly 100 mils of HMP last time, because we know what the density of HMP is. When we make up our hexametaphosphate, that's what HMP stands for. When we make up that solution, we know exactly what goes into it. So since we know the molecular weights of everything that goes in there, we know exactly what the density is going to be. And if we use pure water, we know what the density of that is, which is pure water, so it has zero density. So using that principle, and then using a equation called Stokes' law. Stokes' law basically predicts the settling rate of particles of different sizes. As I said, sand, silt, and clay are particles of different sizes, and sand, silt, and clay is what makes up any soil sample. Some proportion of sand versus silt versus clay particles. So what we're going to do there, using this equation, Stokes' equation, we're going to basically predict, since we know the density of our solution, the water and HMP mixture, since we know the density of the solution, using that equation, we can actually use the hydrometer, this device right here, which measures density of solution. If we use Stokes' law and this hydrometer, which measures the density of solution, if we take measurements in our solution of known density at exact times, then we can actually calculate the density of our solution. And we can equate that to the size of particles that have fallen out of suspension. You'll see what this looks like in real time, if you will. But that's the principle behind what we're doing. So what's important is, as I said, to know what the solution is made of, what the density is, get the exact amounts of soil, the exact amount of HMP, and everything else has to be distilled or purified pure water, right? And then, knowing that, everything's going to be the same. When we measure the density at a given time, we will know by plugging the data into Stokes' law the proportion of sand and the proportion of clay remaining in the suspension. Does that make sense? Hopefully it will. If not, the visual will probably help you understand what we're doing there. Okay, I'm going to go ahead and put this hydrometer down. And again, here's my two solutions, or my two samples, I should say. What I have over here is two 1,000 millimeter flasks. The best ones actually for this are not these plastic ones. The best ones are glass. A lot of the best ones don't have a little lip on them. The glass is great because you don't have all this confusion down here, the different gradations. You just have a mark at 1,000 mils. 1,000 mils is important because that's the total measurement that this equation is going to need, or we're going to need to reference. So here's how we do it. Let's just take the first one here. I'm just going to shake it up because remember, we know exactly how much is in here as far as soil sample. There's 40 grams of soil sample, if you remember. I'm going to go ahead and try to wipe that off just a little bit. You can see it's pretty clean. It's just water in there. So now I'm going to carefully do this. I can pick this up in my hand, and I'm just going to pour it in, just like that. Try to get it all in there. And you can see that I didn't get it all in there yet because it's not clear in here. So I go ahead and take this. Remember, I'm good. I can add as much water as I need till I get to exactly 1,000 mils. So what I can do is I can squirt this, add a little bit of this liquid in there. It's distilled water again. That's what I have to use, and I can go ahead and pour it in like that. So it's kind of a difficult, not difficult, tedious process. It can be. Got to be careful that you kind of rinse it out and keep it tilted into the cylinder. But eventually you'll go ahead and get it. So that's actually, well, I can see still a little bit more in there. What you'll find out is some of the sand particles will stick to the side. So we're actually pretty good. If you look at that, it's pretty good. I might have just a tiny fraction of something in there. I can try it again a little bit more. All right, so I've got all my sample in there, but I need to bring it up to 1,000. So I'm going to take this. I've already prepared this. This is just purified DI water, distilled water, whatever we're using. And I'm going to go ahead and pour this up. And you can see this 1,000 mil mark. I'm just going to go ahead and pour it in there until I reach that, or until I get close, and then I'm going to use that squirt bottle to actually do the final little bit. So I'm getting kind of close now. I'll slow it down. See, if I go over the top, I've kind of messed this thing up. So you're actually kind of better just to be real careful, and then stop there, and then I'll go ahead and use the squirt bottle, and I can actually get anything on the edges. And you can see that I'm not quite there yet. All right, I think I'm right on that mark now. So there we go. There's one sample prepared. I'm going to go off camera and I'm going to prepare the other sample. Then I'm going to show you what's the next step is to actually run these things. So we have one sample ready to go. Okay, here we go. We've got our two samples, and you'll notice we actually have another sample here in the middle. But this sample is clear. What's up with this sample? Well, there's going to be an error associated with every experiment, correct? So what we've done with this particular clear sample, this is our blank. Now what is a blank? A blank is basically going to catch our errors, whatever errors we might have in this particular one here, whether we got some contamination in our water or something like that. This one should pick it up. That's what we're going to use this one for. So one of the other inputs to this Stokes law is we need to know what the temperature of the solution is. So we could actually run this experiment, and if we ran it, and today it's kind of warm in here, but if we ran this experiment in the middle of winter time, it would be the density of this liquid would be different just based on the fact that we have a different temperature. That changes the density of the liquid in here. So we really don't know how the temperature is going to affect us, but we have a correction factor for that. So the important thing for us to do is for us to go ahead and measure the temperature. Now these have all been sitting here at the same time. The water in them is all the same source, so we know they're all the same temperature. I can go ahead and put this in like this. I'm going to suspend it like this. I'm going to do this afterwards, but this is what I'm going to eventually do. You'll see this. I just got this piece of wire there just so it can kind of hang there, and I can actually read the temperature in that one. I'm not quite ready to do that one yet. You'll see that in the end there, but this temperature here is going to represent the temperature of everything, because remember, everything's been sitting and equilibrating in this room for a long time. The samples have been running for like a week now, right? Since the last video we did. So we've got plenty of time for them to all be the same temperature. So now I'm going to show you what's going on through here. How do we actually run this experiment? If you'll notice here, you can kind of see this one's a little bit easier to see, this sample. Do you see how it's light up here? It's light, and then it's darker here at the bottom. If you actually zoom in, I don't know if you can zoom in and see that, but you can actually see what looks like sediment here at the bottom. That's exactly what that is. That is sand and silt that's actually settled to the bottom of this. This is exactly what Stokes' law is actually calculating. What we want to know is how much of that stuff at the bottom there is actually sand, how much of it is silt, and whatever left in suspension is going to be our clay. We need to calculate that. So I'm going to use this device here, this little homemade device. It's got some holes in the bottom, and it's got a plate that's the diameter of these cylinders, more or less. And what I'm going to do with that, the holes are so the water will flow through it, because I'm going to actually use this little device to actually get everything into suspension. Now remember, if you'll remember, pardon me, if you'll remember, I said that this Stokes' law is based on everything going into suspension and settling. So for us to be accurate, we need to make sure that we get everything in suspension. So I'm going to twist this thing left and right. You can see me twisting it left and right like this. But what I'm going to do is I'm going to bring it up and down, and sometimes it's better to actually hold the base of this, just if you get too exuberant I'm going to bring it up and down like this, and I'm going to be careful. Now this is where people spill things out the top a lot. You don't need to go all the way up to the top because you're generating enough force. If you just go about halfway up the cylinder, you'll get everything into suspension. So the idea is I can do this all day long, but I don't want to do it all day long. I want to actually watch my clock up there, and I'm going to actually, since I can see a big digital clock, I'm going to actually wait till this gets to almost to 00 at the top of the hour. And then when it does, when it gets to exactly 00, I'm going to be on the upstroke, and I'm going to pull everything out. I'm going to pull this cylinder out then, and then what I'm going to do is I'm going to put the hydrometer in there. And you'll see me do this, and then at exactly 40 seconds, I'm going to read that hydrometer. So you'll see me do that in just a second. So already things have started to settle, so we couldn't put the hydrometer in now, right? We need to go ahead and get this thing back into suspension, and then pull it out and wait for 40 seconds. Me doing this.
Got it.
Now go ahead and film. Oops. So here we are coming up to the top of the hour there. I've got 4 seconds, 3 seconds, 2 seconds, and 1. So I'm taking it out at 0. Tip it a little bit. I know I've got time because I've done this before. Carefully insert the hydrometer. So you don't want to drop it in there. You want to kind of just, it's going to want to come up. You don't know where it wants to settle. So you can see I'm keeping my eye on it. I've still got about 20 seconds. So now it's kind of sitting there. So if you can maybe zoom in on this hydrometer, you can kind of see I've got still a little bit of time there to look at it. So I'm going to start counting. I'm going to start counting where it is. I can see that it says 21, 22, 23, 24. So it's at 24. Let me show you what that actually means through here. So this actually at 40 seconds. Now I've recorded it so I can pull it out. I've recorded it, but you can see there's a mark there. And this is just they're just marks. They're just numbers right through here. These units, but they're calibrated. I forgot what they are. I'll have to look and see what they're calibrated at. But right there is where the top of the water was, the meniscus. Now you remember, water is going to run up the side of this glass tube, but where the top of the water line was right there at 24, right where my thumb is, or my thumbnail is. That was where the water level was at 40 seconds. So that's important to know that. Now, what I'm going to do is I'm just going to let that sit in there because I can. I mean, I don't need to take it out. Now this is our blank. I'm just going to go ahead and drop this one in there. So we could actually do the same thing. I'm not going to do that, but yeah, let me grab a clean one of these things, just so I have a clean one. But what I'm going to do is I'm going to go ahead and I'm going to simulate doing everything the same, right? Whoops, a little drops there. See how you can get inaccuracies no matter. So I'm going to do the same thing. I'm going to make sure that everything is mixed up. Now you can see there's nothing in here. There's nothing in here but solution. But we're just going to make sure that we do the same thing. So here we go. It's going to be 40 seconds here. It's going to be the top of the hour here in just a second. I'm going to go ahead and pull that one out right there at the 00. Tap this thing off to make sure I get whatever's stuck on there back in solution. Now, I've done everything the same except I don't have any soil in this one. So I can go ahead and pop this one down in through there. And you can see this guy's going to settle all the way down in through there like that. Now, it's kind of bobbing. So when it kind of does that, you can kind of put your finger up. Now I got to kind of watch there for that 40-second time to come. I've got about 15 seconds left. So you can see right now this is already settling all the way down. Now this isn't going to, there's nothing to settle. So once that stops bouncing up and down, that's going to be the reading. So the reading is the only thing that's going to change that reading now is if the temperature changes. So that says 1, 2, 3. Looks like it says exactly 3. So our blank is reading 3. That means that off of every reading here, we're going to need to subtract 3 units. 3 units because this is reading 3. Okay, now what else did I tell you? I haven't done this one yet. I'm going to do that one in a second. But I told you that we needed to actually take the temperature of this soil because the temperature is going to be critical to the density. So I can actually stick this one in here. Let's see if you can is that showing up there on the camera down there? Maybe on this side you can see it a little bit better. But we'll wait for it to do a little bit. But right now it's yeah, as I said, it's relatively warm in here. That's reading about 28.5 degrees Celsius. So we're definitely in a warm lab today. So we're going to record these numbers. We're going to record the original number for this particular one, and that was 24. We're going to record the blank, that was 3, and we're going to assign 28.5 degrees Celsius to all three of these temperatures, all three of these samples at the 40-second reading. So you said, okay, well, I haven't done this one yet, I know that, but I'll do that in a second. But so you might be wondering, okay, you've said 40 seconds, but so you still have the hydrometer here, what's going on? Well, 40 seconds is the amount of time that Stokes' law says particles of a sand-sized diameter need to fall out of suspension. And if you look at this first sample again, you can see it's already clearing at the top. It's much darker down here than it is up here, and it's only been a couple minutes. What we're going to do to really figure out we'll have the sand value now, but what we're going to figure out is that everything left in solution right now after 40 seconds is silts and clays. Our next reading has to be within a minimum of 2 hours. Ideally, we want to wait for 3 hours. But and if you're doing this for some labs, they actually have a whole bunch of intermediate readings as well, and they pick up different kinds of silt and whatnot. We're really interested only in the sand and the clays, right? So that's what we're going to measure. And so we're going to go ahead. I'm going to go ahead and do this one, and we'll get this one going. I guess you don't need to see it, but I'll tell you what happens after the fact. And then we're going to go ahead and wait our 3 hours, and we're going to see how the readings have actually changed. Okay? All right, well, here we are 3 hours later, and you can see there's quite a change to our samples. Here's our first sample, and there's our blank, and then here's our other sample that you didn't watch me do. But you can see there's quite a bit of difference. Let's go ahead and zoom in on this first sample here. You can see the hydrometer in there, and you can see that it's almost clear. So what do you think that might tell you? I'm going to go ahead and zoom in on the stuff on the bottom, see if you can see the sediment pretty well. And if you look closely, you can actually tell that there's different sizes of that sediment, with the coarsest sediment on the bottom and the finest sediment on the top. And if you look just above that, it looks like it's just a little cloudy, which means that there could possibly be a little bit more stuff falling out. But by and large, it looks like everything's fallen out in this 3 hour period. So I'm going to go ahead and move back and show you this other sample, the other one here. I'll zoom back on that one. You can see on the top of this one that there's a little bit of clearing up there. It looks a little bit different, but pretty much all the way down this column, it looks pretty much the same. There's still a lot of material that's left in there after the 3 hour period. Let's go ahead and focus in on the bottom and see what we can see down there. Well, we can still see sediment down there. It looks a little bit more consistent in size. There's a little line of dark on the top, which might be some finer sediments, but there's some material that's still left suspended. So this is actually pretty cool to look at these two different contrasts. Try to get this just right for you guys. Try to get these two different contrasts, because we've really got something that's completely cleared out, which means that there's really very little clay in this, because the only thing that's going to remain in suspension after 3 hours is clay. So clay, if we've dispersed it properly with our HMP, is too light to actually settle out of solution. So a properly dispersed clay will actually remain in solution pretty much forever. It really will not ever settle. And I think that's kind of what we have going on over here in this darker colored one. We have a lot more clays sitting in this soil. If we came back here 24 hours later, it would probably be a little bit clear, but it wouldn't look anything like that other sample. So let's go ahead and just move around this direction and see if we can read the hydrometer on this first one. Well, look at that. I don't know if you can see that, but it looks like it's pretty much sitting at, let's see if I can focus that. Look at that, sitting at 0 right there. It's barely reading anything. So that's actually pretty interesting that we've got something that's that low. and we can see our blank here. We're looking at our blank. Our blank has pretty much stayed the same. We might actually have, let me see here. Yeah, our blank, I'm going to move it around just a little bit. Our blank is sitting a little bit closer to 0 too, and that's a lot of that has to do with, we can't really see it, but a lot of that has to do with the fact that the temperature in the room has changed. So what we would do on this one is we would actually put the actual reading of this. We'd put like a 2 for the blank and a 0 for the other one, and then over here we've got something that's we didn't really give the first one, but we've got a reading that's about 3 or 4 on this one as well. So this is the way you would actually do this. Obviously lots of different samples are going to come up with lots of different readings, and the purpose of this video was just to kind of show you exactly what the procedure is and to kind of give you a visual of what it looks like with different textures, different particle types of soil samples. So what you'll get is to do this exercise, obviously we have to do it for you, but we'll go ahead and post some data sets, and you'll have an idea now how this all works. And with the data sets and the information and the equation that I give you, you'll be able to figure out what the texture of different soils is. All right, that's it for this time. We'll see you for the next video.